Hypertrophy is an increase in the size of whole muscles, and each muscle contains many thousands of muscle fibres. Theoretically, therefore, a whole muscle could increase in size either by increasing the number of fibres or by increasing the size of each individual fibre. Now, although there is some animal evidence that muscles can increase in size by increasing the number of fibres, most research in humans indicates that the main contributor to increased whole muscle size is an increase in the size of each muscle fibre, and that occurs predominantly by the fibre increasing in diameter, although it can also increase in length. During muscular contractions, muscle fibres are activated in groups called motor units, and the central nervous system recruits motor units in order to perform any given task. And the more difficult the task, or the harder the task, the more motor units are recruited, and that means the more muscle fibres are activated. And very importantly, the number of muscle fibres that are controlled by each motor unit is not the same. So low threshold motor units will only control a small number, perhaps 10 or 20 muscle fibres, but high threshold motor units could control up to 2,000 muscle fibres. So the number of muscle fibres that are controlled by any given motor unit differs quite a lot, which means that the potential for muscle growth is much greater in the high threshold motor units than in the low threshold motor units, because an increase in diameter of 2,000 muscle fibres will have a lot bigger impact on the size of the whole muscle than an increase in the diameter of 10 or 20 muscle fibres. We now know that there are at least 3 ways in which we can increase the number of motor units that are recruited in a given muscular contraction, and therefore increase the number of muscle fibres that have been activated. These are an increase in the level of voluntary force, an increase in the voluntary velocity, and an increase in the proximity to muscular failure during a fatiguing contraction. And overall, what ties all of these 3 things together is that the voluntary effort in each of them is higher when motor unit recruitment is higher. And in fact, researchers have managed to link a sense of effort with an increase in the level of neural drive from the central nervous system to the muscle. So in general, it seems that motor unit recruitment increases as we increase our effort in any given contraction, and whether that means that the motor units are recruited in order to produce a greater force, or whether the motor units are recruited in order to move faster, or whether the motor units are recruited in order to complete a very fatiguing contraction when we are reaching the end of our ability to continue with the movement. It doesn't really matter. What matters is that our effort is increased, and therefore the number of motor units that are recruited also increases. Originally, it was believed that only heavy strength training would produce muscle growth, but we now know that both heavy strength training and light load strength training to muscular failure both cause muscle growth, and in similar amounts. And what's very interesting about this is that both of these types of training involve the recruitment of high threshold motor units and the activation of all of those muscle fibres that can contribute to hypertrophy. But what's also interesting, and something that is not really often appreciated, is that high velocity strength training, power training, also involves the recruitment of high threshold motor units and the activation of their muscle fibres, but it doesn't cause any muscle growth. And so clearly, simply recruiting the motor units and activating the muscle fibres doesn't do the job. It doesn't actually get us the stimulus that we need to produce muscle growth. There needs to be something else that's happening, and that is the force-velocity relationship. So the force-velocity relationship is that as each muscle fibre shortens more quickly, it produces less force. So in a high velocity contraction, when all of the motor units are recruited and all of the muscle fibres are activated, the force is still low, and that's because each muscle fibre is producing a low force because of the force-velocity relationship. In contrast, during heavy strength training, we are activating all of our muscle fibres because all of the motor units are recruited in a very heavy lift, and the muscle fibres are shortening very slowly, and therefore they're all producing a very high force. And it's this high force that the slow fibre shortening velocity allows us to produce that creates the mechanical loading that stimulates muscle growth. During light load strength training to failure, the muscle fibres that are controlled by high threshold motor units experience a very similar, if not identical, stimulus to during heavy strength training. And this is because as we approach the end of a set and fatigue is increasing, then our effort must increase in order to continue performing the exercise, and therefore motor unit recruitment increases. This means that the high threshold motor units are recruited and their muscle fibres are activated, but also because fatigue is present, then muscle fibre shortening velocities are reducing, and this allows the muscle fibres to produce greater forces, and this means that they experience higher levels of mechanical loading. Now, obviously, the overall force produced by the whole muscle is much lower than it is during heavy strength training because the external load is lighter, but that doesn't matter as far as the individual muscle fibre is concerned. The individual muscle fibre only responds to the level of force that it produces. And since it produces a high force because the shortening velocity is slow, then it experiences a high level of mechanical loading, which is what triggers muscle growth. This is possible because the stimulus that creates hypertrophy is the mechanical loading of the individual muscle fibre and not the whole muscle, and also because fatigue occurs to individual muscle fibres and not to the whole muscle. So as the set of light load strength training to failure continues, fatigue occurs in the working muscle fibres. But as each individual extra motor unit is recruited, it's recruited fresh and is capable of producing whatever force that it can according to the overall shortening velocity of the muscle. And since the shortening velocity of the muscle is generally slow towards the end of a set of strength training to failure, the muscle fibres of the newly recruited motor units are capable of producing very high forces and therefore experiencing very high levels of mechanical loading. Obviously, as those motor units and their muscle fibres later fatigue towards the end of the set, the level of mechanical loading that some of them experience decreases because of fatiguing processes inside those muscle fibres that impair the function of force production. But at the point when they're recruited, during the fatigue and contraction, they are capable of producing high forces, and this is the mechanical loading that causes hypertrophy.